Welcome to Physics for Aviation Maintenance Technicians. In this module, we will explore essential physics concepts that directly apply to aircraft operation, performance, and maintenance. From matter and energy to gas laws and aerodynamics, this course lays the foundation for safe and effective aircraft service. We begin with matter, defined as anything that occupies space and has mass. Understanding matter and its interaction with energy is vital for analyzing forces, motion, heat, and pressure, all of which are present in aircraft systems. Atoms are the basic building blocks of matter. Each atom contains a nucleus composed of positively charged protons and neutral neutrons, with negatively charged electrons orbiting the nucleus. These atomic properties influence material behavior under stress, heat, and pressure, critical considerations in aircraft materials. Each element is defined by its atomic number, the number of protons, and its atomic mass, which includes both protons and neutrons. Technicians must be aware of elemental properties, particularly in metallurgy, corrosion control, and composite materials. Matter exists in different states: solid, liquid, and gas, with plasma as a fourth state under extreme conditions. Solids maintain shape and volume, liquids retain volume but not shape, and gases have neither fixed shape nor volume. These differences affect fluid flow, structural design, and system containment. Mass is the amount of matter in an object. Weight is the force of gravity acting on that mass. Mass remains constant regardless of location, while weight changes with gravitational force. This distinction is crucial when calculating loads, balance, and fuel requirements under varying altitudes and planetary conditions. Density is the mass or weight of a substance per unit volume. Temperature and pressure influence density. Increasing temperature reduces density, while increasing pressure increases it. Density calculations are essential for fuel management, fluid systems, and aircraft performance. Specific gravity compares the density of a substance to an equal volume of water or air. It is dimensionless and helps technicians understand fluid behavior in fuel, oil, and hydraulic systems. For gases, the comparison is made against air. Let's apply specific gravity. Given water's specific gravity is 1.000 and its weight is 0.0361 pounds per cubic inch, a fluid with a specific gravity of 1.123 weighs 0.040543 pounds per cubic inch. These types of conversions are vital in hydraulic system design and troubleshooting. Energy is the capacity to do work. Potential energy is stored due to position, distortion, or chemical state. Kinetic energy is the energy of motion. Aircraft systems convert energy between these forms. For example, fuel stores chemical energy that becomes kinetic energy during flight. Kinetic energy is the energy a body possesses due to its motion. All moving parts in an aircraft, including propellers, turbines, and control surfaces, rely on kinetic energy. It's a central concept in dynamics and system response. We measure energy in several units. Horsepower, 33,000 foot-pounds of work per minute. Joule, work done by 1 newton of force over 1 meter. Watt, a unit of power equal to 1/746th of a horsepower. These units are critical when evaluating engines, motors, and system performance. Work equals force times distance and is measured in foot-pounds or inch-pounds. Power is work done over time. Understanding these terms helps maintenance personnel evaluate hydraulic actuators, flight control movements, and mechanical linkages. Force can be manipulated using mechanical advantage tools like levers, inclined planes, pulleys, and gears. By altering the distance over which force is applied, we reduce the required effort, a concept heavily used in aircraft jack systems and control surfaces. There are 3 types of levers. First class, fulcrum between effort and resistance. Second class, load between fulcrum and effort. Third class, effort between load and fulcrum. Understanding levers is essential for troubleshooting landing gear, flight controls, and control rods. Let's define some key terms. Moment, the turning force or torque. Fulcrum, the pivot point around which the lever rotates. Grasping these definitions allows accurate diagnosis of mechanical imbalance and actuation issues. In a first-class lever, like a seesaw, the fulcrum is centered. If you place 120 pounds at a distance of 10 feet on one side and 60 pounds at 20 feet on the other side, the lever balances. This calculation is key in determining load distribution and system response. This slide encourages exploring alternative ways to visualize and calculate the function of a first-class lever. Using diagrams and value substitution enhances your understanding of mechanical advantage, a skill essential for interpreting aircraft maintenance schematics and technical manuals. A second-class lever places the load between the effort and the fulcrum. A common aviation example is the wheelbarrow-like motion seen in some cargo loading systems. In this configuration, the mechanical advantage is always greater than 1, reducing required input effort. A third-class lever places the effort between the load and the fulcrum. The force required is greater than the resistance, but it allows for increased speed and range of motion. Many flight control linkages, such as those used in flaps or trim tabs, are third-class levers. In a third-class lever, the effort applied is always greater than the resistance, but what is gained is speed and distance of movement. This trade-off is valuable in systems where responsiveness is prioritized over mechanical advantage. An inclined plane allows us to move loads vertically with reduced force over a longer distance. This principle applies directly in loading ramps and slide-out tool trays used in aircraft hangars and cargo operations. Whether you lift a 500-pound object vertically or slide it up an inclined plane, the work performed is the same, 2,000 foot-pounds. The inclined plane reduces required effort but increases distance. The law of conservation of energy ensures that work remains constant. A pulley is used to lift or lower loads and redirect force. The more pulleys added, the less effort required, but over a greater distance. Pulleys are fundamental in hangar hoists, rigging systems, and even aircraft cable routing. Mechanical advantage, MA, measures the force amplification achieved by a machine. MA of 1, effort equals load. MA of 2, effort is half the load. MA of 4, effort is 1/4 the load. However, the work done remains the same. The only thing that changes is the required input force and distance over which it's applied. Gears transmit torque and motion between rotating shafts. They are found in aircraft engines, landing gear systems, and instrumentation. There are several gear types, each with its own function: spur, bevel, worm, and planetary gears. An internal spur gear meshes with another gear inside its diameter. Both gears rotate in the same direction. This type of gear setup can be found in planetary gear systems commonly used in turbine engine reduction gearboxes. In contrast, external spur gears rotate in opposite directions. This configuration is simple and effective for transmitting power, and is commonly used in accessory gearboxes and mechanical drive systems. Beveled gears change the direction of applied force, often by 90 degrees. These gears are widely used in aircraft components where rotation needs to be redirected, such as flap actuators and control surface interfaces. Worm gears provide a high mechanical advantage and allow for precise control. They're used where space is limited or where self-locking is beneficial, such as in flap and trim systems. This diagram illustrates a planetary gear system, commonly used in aircraft engines and transmissions for torque conversion and speed control. At the center is the sun gear, which engages with multiple planetary gears that rotate around it. These planetary gears are supported by a rotating carrier and mesh with the outer ring gear, which remains stationary or rotates depending on the configuration. The interaction between these gears allows for various gear ratios, enabling increased torque or speed reduction without large gear assemblies. Planetary systems are valued in aviation for their compact size, load distribution, and efficiency under high-power conditions. Let's apply gear ratio math. A drive gear with 1,728 teeth turning at 400 RPM is meshed with a driven gear with 144 teeth. Using a 12:1 ratio, the driven gear will rotate at 4,800 RPM. Smaller gears rotate faster. This is fundamental in designing speed reduction or increase systems. Stress is defined as the force applied over a given area. It is measured in units such as pounds per square inch. Understanding how stress is distributed helps us determine material suitability for structural components, fasteners, and pressurized systems. This illustration shows the 5 primary types of stress that materials experience in aircraft structures. A. Tension occurs when a force pulls a material apart, stretching it along its length. B. Compression is the opposite. Forces push inward, trying to shorten or crush the material. C. Torsional stress results from twisting forces that rotate the material in opposite directions. D. Shear stress happens when two opposing forces slide past each other along the same plane. E. Bending stress is a combination of compression and tension. Compression acts on the inside of the bend, while tension occurs on the outside. Understanding these stresses is critical to ensuring aircraft components can handle operational loads safely and reliably. Strain is the deformation caused by stress. According to Hooke's law, if the strain is within the elastic limit, it is directly proportional to the stress applied. This principle is used in designing engine shafts, wing spars, and detecting structural fatigue. Newton's laws of motion apply directly to aviation physics. First law, inertia. Objects resist changes in motion. Second law, acceleration. Force equals mass times acceleration. Third law, action and reaction. For every action, there is an equal and opposite reaction. These laws govern aircraft motion, stability, and propulsion. Speed is the rate of motion regardless of direction, while velocity includes direction. For example, 200 knots is speed, while 200 knots heading east is velocity. Accurate understanding is vital for navigation, airspeed indication, and inertial reference systems. Remember, stress is force per unit area, and its proper evaluation is crucial for load-bearing components in airframes and engines. In circular motion, two forces are at play. Centripetal force pulls the object toward the center of the circle. Centrifugal force is the apparent force that seems to push outward. These concepts help explain turn coordination, tire dynamics, and gyroscopic instruments. This section introduces the core principles of gas and fluid mechanics, which include the effects of heat and pressure, gas laws, and the behavior of sound. These principles are essential for understanding fuel systems, hydraulics, pneumatics, and cabin pressurization. Heat energy is a form of energy transferred between substances due to a temperature difference. 1 British thermal unit, BTU, equals 778 foot-pounds of work, 252 calories, or approximately 1,055 joules. Latent heat refers to the energy required for a phase change, such as fusion, solid to liquid, vaporization, liquid to gas, sublimation, solid to gas. These changes are common in fuel vaporization and anti-icing systems. When heat is applied to a material, its molecules move faster, increasing volume. For example, the SR-71's engines expand by 6 inches in length and 2.5 inches in diameter during flight. Understanding this expansion is critical for component clearances and stress limits. Thermal expansion is calculated using the formula E equals K times L times delta T, where K is the coefficient of linear expansion, L is the original length, and delta T is the temperature change. For example, an aluminum rod 2 feet long, heated from 25 degrees Celsius to 30 degrees Celsius, will expand by 0.00024 feet. Small changes like these are significant in precision aircraft structures. Specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water has a baseline value of 1.000. Materials with lower specific heat warm up faster, a key factor in material selection and thermal protection. There are 3 basic methods of heat transfer: conduction, through direct contact between materials; convection, through the movement of a heated fluid; radiation, via electromagnetic energy without direct contact. Understanding these methods is vital for designing cooling systems and thermal insulation. Temperature is a measure of the average kinetic energy of molecules in a substance. It is measured using different scales: Fahrenheit, Celsius, centigrade, Kelvin. Rankine-accurate temperature measurement is essential in engine monitoring, system calibration, and flight planning. This slide offers a visual reference for comparing temperature scales. For FAA exams and fieldwork, you must be familiar with these scales, especially Celsius and Kelvin, which are commonly used in scientific and maintenance documentation. To convert temperature from one scale to the other, we use the following standard formulas. Degree F equals 1.8 times degree C plus 32. Degree C equals degree F dash 32 slash 1.8. Degree K equals degree C plus 273. Degree R equals degree F plus 460. Example, 45 degrees Celsius equals 113 degrees Fahrenheit. 85 degrees Fahrenheit equals 29.4 degrees Celsius. Knowing how to convert temperatures is essential for interpreting engine and environmental data. Pressure is the force applied over a given area. It's measured in pounds per square inch, SI, millibars, inches or millimeters of mercury. Understanding pressure is critical in fuel systems, hydraulics, and cabin pressurization. On a standard day, sea level pressure is 29.92 inches of mercury, or 14.69 psi, and the temperature is 15 degrees Celsius or 59 degrees Fahrenheit. These baseline conditions are used in aircraft performance charts and FAA test questions. There are three types of pressure readings: PSIA, absolute pressure; PSID, differential pressure; PSIG, gauge pressure. Technicians must understand which type is being referenced when calibrating instruments or servicing systems. When solving pressure problems, convert gauge pressure to absolute by adding atmospheric pressure. Convert absolute pressure to gauge by subtracting atmospheric pressure. Example, 15.6 psig equals 30.3 psia. Use absolute values in all calculations unless otherwise stated. Let's now discuss the gas laws, starting with Boyle's law. Boyle's law states that when temperature is held constant, the pressure of a gas varies inversely with its volume. If volume decreases, pressure increases, and vice versa. This principle is vital for understanding pressurized systems and oxygen bottles. Charles' law says that gas volume or pressure changes directly with temperature, assuming the other factor is held constant. This explains how tire pressure rises during flight as the air inside heats up. The general gas law combines Boyle's and Charles's laws. P1 V1/T1 equals P2 V2/T2. This equation is used to calculate pressure or volume changes in systems like oxygen tanks and pressurized cabins when temperature fluctuates. This slide demonstrates how to apply the combined gas law when volume remains constant. First, we list the given values, initial volume and pressure, as well as the temperatures in Celsius. Next, we convert the temperatures to Kelvin and convert the pressure from PSIG to SIA by adding atmospheric pressure, 14.7 psi. Then, we plug the absolute values into the equation. P times T/T equals P, since volume is unchanged. Solving this gives us a final pressure of 160.13 SIA, or approximately 145.43 psig. This method is essential when calculating pressure changes due to temperature variations in sealed aircraft systems. Always verify you've solved for the correct unit, whether PSIG, PSIA, Celsius, or Kelvin. This attention to detail is a must when servicing or troubleshooting pressurized systems. Let's now focus on fluid mechanics. Fluids include liquids and gases, both of which flow and take the shape of their containers. These principles apply to hydraulic, pneumatic, and fuel systems across all aircraft. The pressure at the bottom of a fluid column depends on the height and density of the fluid, not the total volume. This principle is used in designing and servicing fuel tanks and reservoirs. For example, given a tank with a depth of 18 inches and a specific gravity of 0.72, the pressure at the bottom is 0.468 psi. These calculations are routine in fuel system design and troubleshooting. Buoyancy is the upward force that supports an object in a liquid. As explained by Archimedes' principle, the object displaces fluid equal to its own volume and is supported by the weight of that displaced fluid. For example, a 60-pound block displaces 62.38 pounds of water. Since the buoyant force exceeds the block's weight, it floats. These calculations are critical in understanding float-type carburetors and emergency flotation devices. How do you stop 300,000 pounds of aircraft? This question highlights the efficiency of hydraulic systems. A small input force, such as 15 pounds from a pilot's foot, can stop a 300,000-pound aircraft using hydraulic principles. This is made possible by Pascal's law and mechanical advantage. Pascal's law states that pressure applied to a confined fluid is transmitted equally in all directions. This principle forms the foundation of aircraft hydraulic systems, enabling the amplification of force to operate landing gear, brakes, flaps, and more. This diagram shows the fundamental relationship between force, pressure, and area, critical to understanding hydraulic and pneumatic systems in aviation. The basic formula is force equals pressure times area, shown in the red circle. To find area, divide force by pressure, as shown in the blue section. And to find pressure, divide force by area, illustrated in yellow. These triangle charts make it easy to remember and rearrange the equation, helping technicians solve for any missing value during system analysis or troubleshooting. This diagram represents the relationship between volume, area, and distance, which is often applied in hydraulic systems and tank capacity calculations. The primary formula is volume equals area multiplied by distance, illustrated in green. To solve for area, divide volume by distance, as shown in blue. To find distance, divide volume by area, highlighted in orange. This triangle tool simplifies rearranging the formula, helping aircraft maintenance technicians quickly calculate fluid displacement, piston stroke lengths, or actuator volumes with confidence and accuracy. This diagram demonstrates the basic principle of hydraulics. Pressure is transmitted equally in all directions within a confined fluid. On the left, a small piston with an area of 1 square inch receives a force of 1 pound, creating a pressure of 1 psi. That same pressure is transmitted through the fluid to a larger piston on the right, which has an area of 10 square inches. Since force equals pressure times area, the output force becomes 10 pounds, 10 times greater than the input force. This shows how hydraulics can multiply force, a principle widely used in aircraft landing gear, brakes, and control actuators. This diagram demonstrates how piston and rod area differences affect force output in a hydraulic actuator. The piston area is 4 square inches, and the rod area is 1 square inch. When 1,000 psi is applied to the piston side, it produces 4,000 pounds of force, because force equals pressure times area. On the rod side, however, the effective area is reduced to 3 square inches, 4 minus the 1 square inch rod, so the resulting force is 3,000 pounds at the same pressure. This principle is crucial in designing actuators for directional control, retraction, and extension, where unequal forces are required. Daniel Bernoulli discovered the relationship between pressure and velocity in a fluid. His principle helps explain lift, airflow in carburetors, and thrust in turbine engines and propellers. All critical concepts for maintenance technicians. A Venturi tube demonstrates Bernoulli's principle. As fluid velocity increases through a constriction, pressure decreases. This concept applies directly to carburetors, airspeed indicators, wings, and turbine blades. This diagram illustrates how Bernoulli's principles relate to the aircraft wings. As air flows faster over the top surface of the wing, pressure decreases, generating lift. The decrease in pressure is accompanied by a temperature drop, a factor in wing icing and anti-icing system design. Propellers generate thrust by creating a low-pressure area in front of the blades. Bernoulli's principle explains how air accelerates over the curved blade surfaces, reducing pressure and pulling the aircraft forward. Turbine blades also utilize Bernoulli's principle. As the curved blades accelerate airflow, they produce a pressure differential that generates thrust. Proper blade design is essential for engine efficiency and performance. In carburetors, the Venturi effect draws fuel into the airstream. As air accelerates through the narrow section, pressure drops, causing fuel to be drawn from the float chamber into the combustion airflow. This principle is vital in understanding mixture control and engine performance. Sound is a pressure wave caused by the vibration of an elastic medium. It travels in all directions and is measured in decibels, dB. Exposure to excessive noise can cause damage, making hearing protection vital in aircraft maintenance environments. Frequency is the number of wave cycles per second, measured in Hertz, Hz. A higher frequency results in a higher pitch. This concept is critical in acoustic inspection tools and interpreting warning systems. The Doppler effect explains the change in frequency and pitch as a sound source moves relative to the observer. In aviation, this principle is used in weather radar and navigation systems to interpret motion and velocity. At sea level, The speed of sound is approximately 760 miles per hour, or 661.7 knots. The speed of sound varies directly with temperature, meaning compressibility effects are encountered sooner at higher altitudes, where it's colder. As an aircraft approaches the speed of sound, air compression effects create resistance known as the sound barrier. This is where aerodynamic heating and shock wave formation become significant. A stationary source emits sound waves evenly in all directions. This slide sets the stage for understanding how sound changes when the source is in motion. At Mach 0.7, the sound waves compress in the direction of motion and spread out behind, resulting in a Doppler shift. This shift has practical applications in navigation and radar systems. At Mach 1.4, the aircraft is traveling faster than the sound it generates, creating shock waves and a sonic boom. Supersonic flight introduces new aerodynamic challenges including heating and stability. Mach number is the ratio of aircraft speed to the speed of sound. Subsonic, less than 0.75 Mach. Transonic, 0.75 to 1.2 Mach. Supersonic, 1.2 to 5.0 Mach. Hypersonic, greater than 5.0 Mach. Understanding Mach number is essential for interpreting performance data and aerodynamic behavior. Above Mach 3, aerodynamic heating becomes a major concern. High-speed aircraft must use specialized materials and designs to manage thermal expansion and heat stress. At Mach 9.6, extreme conditions exist where temperature, pressure, and airflow behavior change significantly. This slide serves as a reference to the outer limits of current aerospace capabilities. Compression waves form at supersonic speeds, resulting in shock waves that affect lift, stability, and control. Aircraft structures must be designed to manage these forces. The Concorde was the only commercial supersonic airliner. Despite its technological achievement, it was retired due to economic and environmental challenges, highlighting the balance between innovation and practicality in aviation. Compression waves form at supersonic speeds, resulting in shock waves that affect lift, stability, and control. Aircraft structures must be designed to manage these forces. This section transitions into aerodynamics, exploring how air interacts with the aircraft. Factors such as density, humidity, and temperature all impact performance, lift, and drag. Standard day conditions of the atmosphere provide a baseline for aircraft performance calculations. The standard day temperature is 15 degrees Celsius. Pressure is 29.92 inches of mercury. These values are used in maintenance manuals and performance charts to ensure consistent measurements. Air density is mass per unit volume. Lower density reduces engine performance, lift, and payload capacity, requiring longer takeoff distances and affecting climb performance. Humidity is the amount of water vapor in the air. Since water vapor is lighter than air, increased humidity reduces air density, which can adversely affect aircraft performance. Dew point is the temperature at which air becomes saturated and water vapor condenses. If the temperature drops below this point, visible moisture forms. This has implications for carburetor icing, fuel system ventilation, and structural icing. As Albert Einstein said, all of science is nothing more than the refinement of everyday thinking. This course has equipped you with a solid understanding of applied physics and aviation. Knowledge you'll use every day as a maintenance technician, ensuring airworthiness, safety, and compliance.